I will continue giving lectures on infinity category. And last time we talked about adjoint functors and presentable infinity categories. So today I will talk about stable. There are three topics. The first, I will talk about stable infinity categories. What does it mean for infinity category to be stable? Next, I will talk about stabilization, which is a technique that if you give me a good enough or just a good stable infinity category, I can stabilize and get a stable infinity category. So that is like the input is an infinity category. Under very mild assumption, you can stabilize and get an infinity category which is stable, which is the category of spectrum objects in C. And finally, I will talk about the Infinity-Categorical machinery for us to define smash product for spectra, because apparently one of the most important example is for stable infinity category is the category of spectra, the category of spectrum objects in the category of spaces. So I will use the Infinity-Categorical technique to define smash product for spectrum, the category of spectrum, which is the category, you do the stabilization for the category of spaces. All right, so I will start. So the first part is that I will define stable infinity categories. And the idea to keep in mind is that a stable infinity category should like the infinity categorical version of abelian categories. That is, we sort of want to do like, we can do homological algebra in stable infinity categories. And next, our definition will also have advantage that if C is stable infinity category, then its homotopy category is going to be a triangulated category. Of course, this is what we want if we want to do homological algebra. And I would first define what is a stable infinity category, and later I will give some properties and also give more characterizations for like stable homotopy infinity categories. Right. So now let's start with the definition. So first, I think throughout my lecture, C will be an infinity category, and we say an object 0 in C is a 0 object. This is, as you would expect, that this object 0, if it is both an initial object and a final object. So, and if C has a 0 object, which is pointed. If C has a 0 object. And you can imagine if you have a 0 object in this category, you can talk about zeromorphisms. So if you have two objects in C, then the zeromorphism is sort of like if it factors go through this object, 0 object. This is the zeromorphism. And so now suppose that we have a pointed infinity category. And we say a triangle in this category C is just a diagram looking like this. And this is the 0 object, a 0 object. And it could be described by a functor from the product of two delta 1s to C. And in particular, we say this triangle, so it is a little bit weird. This is a square, but we say it is a triangle. And we say this triangle is a fiber sequence if this is a pullback square. I will call it star, is a pullback square. And we say it is a co-fiber sequence if the star is a push-out square. And so, and similarly, we say that a morphism f x to y, if this is a morphism, then the co-fiber of f is going to be something which fills up this as push out square. So this map is called cofiber of F. And dually, you can define fiber of a morphism. Okay, so now I'm ready to give the definition of a stable infinity category. So C is stable if first C is pointed, so it has a zero object. Secondly, C has a cofiber. So every morphism has cofiber and fiber. That is, given any morphism, you can always complete it to a triangle which is a fiber square, as well as you can complete it to a triangle which is a cofiber square. And moreover, these two notions are the same. So a triangle that is cofiber is the same as fiber. A cofiber sequence is the same as fiber sequence. A triangle is a fiber sequence if and only if it is a cofiber sequence. So that's the definition for an infinity category to be a stable infinity category. And some examples. So we will see shortly. So we will see that if C is an infinity category with finite limits, then the infinity category of spectrum objects is stable. In spectrum objects in C. So I will define this shortly. And second example, I'm not going to say too much in detail, but if A is an abelian category, then you can suitably define the derived category as an infinity category, and it will be stable. So these are some examples of stable categories. And now I'm going to talk about some properties of stable infinity categories. So first, that is the main theorem I want to discuss or mention is that if C is stable, then its homotopy category, which is going to be an ordinary one category, is a triangulated category. So recall, or I will briefly mention it, and I believe tomorrow you will see a little bit more detailed discussion on triangulated categories and the other things you can do with them. So categories, now this is some ordinary category. C is triangulated if you have a functor, a self-functor, I will just call it sigma. C maps to itself, and a triangulated category has the following data. First, it has a endo functor from C to itself. Secondly, it has some collection of the so-called distinguished triangles. I'll just repeat it as distinguished triangles, which looks like this, which has the form that X maps to Y, there's a morphism from Y to Z, and then Z goes to the suspension of X or shift of X, depending on the context. And finally, C is an additive category. And together with a lot of axioms. So basically, if you have an abelian category, its derived category will be a triangulated category, and that's one of the prototypes for this notion. And the axioms, if you're interested, you can just search and find the references. So my main theorem for this part is that the homotopy category of a stable infinity category is going to be a triangulated category. So I will sketch the construction as well as some of the applications of this result. So now the input is that we have a stable infinity category. So we want to first, of course, what we want, if we want to verify that the homotopy category is a triangulated category, we want to have the suspension functor as well as we specify what are distinguished triangles. So let's do it one by one. So first, if C is pointed, so the first step, if C is a pointed infinity category with finite colimits, so let me double check if I'm not, okay, sorry, this is wrong. So with cofiber, that is every morphism in C has cofiber. So of course, this hypothesis is satisfied by a stable infinity category. So I'm just trying to minimize the hypothesis I need to present my results. Then the machinery of that's lifting properties, the machinery of Cartesian fibrations, all the things like that, will give rise to a functor called suspension functor from C to C. This is from lifting properties. So this detail, I'm not going to spell it out. I'm just trying to briefly tell you about how you get this suspension functor from the data of infinity category. It is going to be like you map C embedded to some functor category, and there's a section, and you evaluate. So you are trying to connect C with the category from this category, and there you can compose the suspension as some suitable composites. If you're interested, you can. Oh yeah, I forgot to mention that most of the things for the stable infinity category I want to talk about, as well as stabilization. The references I'm going to use is Jacob Lurie's higher algebra. Chapter 1. More precisely, it is section 1.1 and section 1.4. Okay, yeah, so if you want to look for detail, this is one of the places you can go to. And of course, if you work dually, and so that then C is equipped with fiber sequences, then you can also construct a functor. You can construct the loop functor. So I'm going to say some facts. So first, you will always have an adjunction between these two functors if you have the hypothesis that C is, say, a stable infinity category. Sorry. So if C pointed, so I was wrong. So if C is pointed and with fiber and cofiber, and moreover, if C is stable, that is, you have the actual information that a fiber sequence is the same as a cofiber sequence, you will know that they are going to be equivalences of categories. This is making sense because, well, if they're the same, then expect that in this definition, many parts of this definition are saying very similar things because the fiber sequence is the same as a cofiber sequence. Okay, so that's the two facts I can say if I construct these two functors. And that's going to be our first part of data if we want to say verify the homotopy category is a triangulated category. And because you have this adjunction, then you can see that it already gives the homotopy category some additive structure, because you can evaluate the pi naught of the mapping space between two objects. Let's say X and Y are two objects of C. Then this is an abelian group, because you can use the suspension loop adjunction to suspend the first object, so that you have the room to define a group structure. And you can also note that also you have product and finite product and coproduct. Are defined from the information of the suspension loop functor as well as the cofiber and fiber sequence. For example, the coproduct between X and Y could be viewed as the cofiber of this. So this is just some hint about how to do such constructions. So in this theory of stable infinity categories, a lot of tricks are coming from the fact that you can convert different kinds of limits and co-limits, like cofiber, fiber are in particular push out, pull back and push out. Sorry, I was about to say in particularly, I apologize. So, and of course, if you, and also as well as some other construction, you can convert in different notions of limits and co-limits. So that's how you do a lot of tricks and go back and forth between different types of co-limits and limits. All right, so far we have defined this functor, and we also have this is an abelian group, and also you have this. So this already gives you that this two part tells you that the homotopy category is an additive category. And if you want to go to check the triangulated structure, it remains to specify what are distinguished triangles. So they are going to be also, as your intuition would expect. So a distinguished triangle, the collection of distinguished triangles is going to look like this. So I'm just going to record this. So you have this is in the homotopy category of C. So the suspension functor can pass to homotopy category. And in homotopy category of C, you have this sequence of morphisms. And it is a distinguished triangle if and only if it satisfies that all these morphisms are represented by some morphisms in the original categories. So you have a diagram looking like this, where you want such that you have such a diagram where both two squares are push-out squares or pullback squares. And also this element is equivalent to the suspension of X. And that's what you mean by a distinguished triangle. So, and if you collect all these data, distinguished triangle, you can put them together and verify that, verify all the axes, which is of course a painstaking work, but you can check that HC is a triangulated category. With these data as specified. Okay, so that's one of the main results for stable infinity categories. And before I move on to my next topic of stabilization, I just want to say a few more things for stable infinity categories. So, well, let's choose those important things to mention. So we have a notion of stable subcategory of a stable infinity category. So this is very intuitive. You have a full subcategory, which is a full subcategory, and is closed under cofiber sequence and has zero object. And you also have the notion of exact functors. So this is going to be the functors that we are going to be interested in between stable infinity categories. So if you have a functor where C and D are stable, then this functor F is called an exact functor if it stands 0 to 0, the zero object to zero object, and it stands fiber sequence to fiber sequence. So of course, because they are stable, it extends co-fiber sequence to co-fiber sequence because they are the same. And there is a very interesting or a good criteria for you to check the functor is exact. So if, again, the input is a functor between two stable categories, then f is exact is equivalent to f is left exact, and is equivalent to f is right exact. Where exact left exact means it preserves finite limits, and right exact means it preserves finite colimits. So again, you can imagine that the proof of it will involve like some different writing the forms of colimit and limit suitably, so that, for example, you can realize finite limit as coming from a fiber sequence and finite product, which we already sort of mentioned that a stable category has finite product or coproduct. I gave the example of coproduct here. Okay, so that's some the things I want to say about stable infinity categories. And now I'm going to move on to stabilization. That is, how do we construct a stable infinity category from a given infinity category? So of course, this has motivations. One of the motivations is of course coming from classical algebraic topology, from the construction of spectra, and as well as we also saw some motivations from Brown representability theorem, which says that the generalized cohomology theory is going to be represented by something like an omega spectrum. So these are going to motivate us and tell us about how do we define the spectrum objects for an infinity category. So I'm going to because I'm a little bit behind my plan, so I'm not going to talk about Brown representability for infinity categories. But the output of it is basically saying that if you have a generalized cohomology theory, maybe I can just say cohomology theory, on an infinity category, it's roughly going to look like a sequence of functors from the homotopy category of this infinity category to the category of to the opposite category of a contravariant functor from the homotopy category to the category of sets, or maybe it's the same. We can say it's a bit in groups, and such that there are, like, say, equivalences between composed with this suspension factor, and as well as some more axioms, the additive axiom, as well as the some other axioms for cohomology theories. So, and Brown representability theorem will tell you that if you have a cohomology theory on an infinity category C, then these functors, Hns, will be represented by elements in C. So Hn will be represented by elements En in the infinity category C. And this natural equivalence will lead to equivalences in the infinity category C that E of n is going to be equivalent to the loop of E of n plus 1. Of course, here we have some mild assumptions on our category, infinity category C. All right, so this is going to be the most, I think, one of the most important motivations for us to define spectrum objects. So now I'm going to give the definition of spectrum objects. So now we fix C to be an infinity category with finite limits. So, and we have the following definition. So now suppose again, F is a functor between two infinity categories. And we say that F is excisive if C has push out and F sends push out in C to pull back in D. And we say the functor F is reduced if C has final object and F sends final object to final object. And we denote we exploit the following notations. So this EXC C comma D is the category, the full set category, subcategory of the functor category from C to D spanned by excisive functors. And we have FU and star to be the category, full subcategory of reduced functors. And finally, we have EXC star C and D to be the category of course, as we expect, excisive reduced functors. So there is a very interesting trick. So I want to introduce, which is that if, for example, if C is stable, then a functor F is excisive reduced if and only if F is left exact. So here we are using the fact that if C is stable, then the push out is the same as pullback. So it's not only the co-fiber sequence is the same as fiber sequence, but in a stable category, the push out square is the same as the pullback square. So if F is left exact, it will send a push out square in C, which is pullback square as well, to a pullback square in D, because a left exact functor preserves finite limits. And similarly, it sends final object, which is the limit of the empty diagram, to the final object. So this is a good criterion for you to check a functor is reduced excisive if the domain category C is stable. And moreover, if C and D are both stable, then an excisive reduced functor is precisely an exact functor. So you can use the result I just mentioned about the equivalences between this notation. So F is exact is equivalent to F is left exact if the functor is between two stable infinity categories. All right, so the next thing is a fact which I want to mention, which also relates to my talk last week. So if under some mild assumptions, and so maybe not too mild, but if D is presentable, then we have this category, all these categories, EXC, EXC star, and Fung star are presentable. So this is a good fact, because later we want to, so the reason why I need to mention here is like later we'll study presentable stable infinity categories, so that we hope to combine these two good properties to see what we can do and to get some good results and simplify a lot of things. I'll go back to this later. So basically, we sort of mentioned, I believe, last time that if you have a presentable category, then if you map into this presentable category to form the functor category is going to be presentable. And these subcategories are going to be accessible localizations of these presentable categories. So they are still going to be presentable. That's like how you understand this fact. Yeah, all right. So next, I'm ready to define this category of spectrum objects. So first, let's denote by SFIN to be the full subcategory of spaces how do I say it? Well, generated by the final object under colimit, under finite colimit. So basically, you can think about this as the infinity category of finite spaces. And we can also form the co-slice category. Under the final object. So we have this. This is the, you can think about this as the infinity category of pointed finite spaces. And we define SP of C is defined to be the category of excessive reduced functors from this category to C. So that's the main definition for the second part of my lecture. So the category, infinity category of spectrum objects in C is the category of excessive reduced functor from this indexing infinite category of pointed finite spaces to C. All right, so that's our definition. And of course, our hope is to hope that this is going to be a stable category. So the next key result I want to say is that this is the stable category, stable infinity category. So that's why we call this is the stabilization. Okay, so let's see. And don't forget that we always assume that this category C is equipped with finite limits. Okay, so I'm going to sketch the proof of it. So the proof consists of, I think, the following three parts. So first, I'm going to say that this category is pointed and has finite limits. So recall that a category is stable if it is pointed, has and there's equivalently, you can say it is pointed, it has finite limits and co-limits, and push out is the same as pull back, or co-fibering is the same as fibering. So the first step is to say that this is pointed and has finite limits. So it is pointed is easy to check because you can map the zero object to the zero object, and to the final object. Final object of C does not need to have a zero object, and check that this is also an initial object, and it has finite limits because we assume that C has finite limit, and it's in the functor category. You can compute limits pointwise. So this category is equipped with finite limits. And secondly, you want to keep proving things for to verify this stable infinity category. And you can prove that this is stable, that is, you finish the proof, if C is presentable. So that is, you first check things when C is very strong, has a strong assumption that C is presentable. So a presentable category is complete. Is co-complete. So you have the part of the co-limit you need, and there are some machinery which is a little bit more technical, but you can use such machinery to prove that the push out is the same as pull back. Again, just using some lifting properties to check that these two notions are the same. So you can prove that this is a stable infinite category for if the target category C is presentable. And finally, you check in the general case. That is, if C is not presentable, but you can always embed C into the pre-shift category, simplicial pre-shift category over C. And so you have an induced functor from this to this, well, that is the excessive reduced functor to the category of pre-shifts. And you can check that we have already proved that this is stable because the pre-shift category is presentable, as I mentioned last time. And you can use the notion of the criterion to check when will a full subcategory of a stable infinity category be stable. That is, you check this is closed under co-fiber and suspension, something like that. You check some closeness properties, so you can check that this one is a stable subcategory of this. So this one will be stable. Yeah, I'm just giving you a sketch of the proof. So that's the 3 steps you want to do. Of course, it involves a lot more work than I mentioned, but basically the logic goes like this. Yes, so then you can show that for as long as C has finite limit, this is going to be a stable infinity category. So we are done with our goal. That is, we have an idea about this stabilization. And by the way, if you just look at the definition, of course, this category, this one contains those spheres. So if you have those n spheres, you can evaluate the functor at n spheres. You recover the classical notion of defining a spectra spheres. Okay, so yeah, so that's something. And also the equivalence of these constructions were discussed by many authors in their comparison between different models for spectra, at least for the spectrum object for spaces. So indeed, this definition as excessive reduced functor is going to be the generalization of the classical definition of stable homotopy category. Yeah. So next, I'm going to talk about, say a little bit more about, to collect some very important properties of this stabilization. Many of them are generalizations as well as of those classical results. So first we have this infinity loop space functor that is from the category of spectrum objects in C to the category of category C, that is to evaluate at the S0. And of course, you can also define this can also be defined, that is you evaluate as n spheres. So yeah, and I will just record some results. So first, you expect that the following are equivalent, that if you have a start with a stable category, this construction is idempotent. That is, if you do the stabilization of a stable infinity category, of course, you won't get anything new. So the following are equivalent. D is stable, and this infinity loop space functor is an equivalence. So that is, this stabilization functor is idempotent. And there's another proposition which basically tells you that this functor construction is universal. That is, you have an equivalence of categories if you compose with this infinity loop space functor. That is, the category of excessive reduced functor from C to the category of spectrum objects in D is equivalent to the category of excessive reduced functor from C to D, if you compose it with the omega infinity functor. And this is because this one is this equivalent to the spectrum objects in this category. And we also know that this is stable. So this equivalence is because this is stable in some sense. Actually, I didn't mention the most general result, but the most general result is that the category of excessive reduced functor from C to D will be stable if C has finite colimit. Yeah, I just want to complement this, and D has finite limit. Yeah, this is the generalization of this theorem, because of course we know that this category is bicomplete. So we have this is has finite limit and finite colimit. So this satisfies this general statement. Yeah, so these two are two very important characteristic of this stabilization process. And if we use these two results, we can end up having another characterization of stable infinity categories. So this is higher algebra 1.4.2.27. So if C is a pointed infinity category, then the following are equivalent. So this is saying that we know that a stable infinity category is a infinity category that the co-fiber sequence is the same as fiber sequence, but it can also be characterized that it's the sigma suspension functor and the loop functor are respectively going to be equivalences of categories. So the following are equivalent. C is stable. It's equivalent to C has finite colimit. So this is also a hypothesis we want to make if we want to define the suspension functor. And this is an equivalence. And also similarly, it is equivalent to it has finite limit. And the loop functor is an equivalence of categories. Right, so to prove this, we are going to use the proposition I mentioned here, that is, sorry, this one. So one direction is, for example, if we want to prove 1 is equivalent to 3, then one direction is clear, 1 implies 3, we have discussed this. And to prove 3 implies 1, we sort of want to show that, yeah, I want to sketch it. So 3 proves 1 is like, we can think about this category of because C has finite limits, so we can think about, so we know this is a stable category. And we can also think about this as the category of as the homotopy limit of how should I say? Well, an infinite tower of objects in C. And because we know that this loop functor is an equivalent, then we know that this is going to be eventually an essentially constant diagram. So we get this is the equivalence. And this gives us the C state. And you can use the dual argument to prove that item 2 is equivalent to item 3. Okay, so that's the general discussion for stabilization. And next, I want to go down a little bit and say a few simple facts for our most interesting example, that is the category of spectrum. The category of spectrum objects in the category of pointed spaces. And so I just mentioned that first, this homotopy category is equivalent to the stable homotopy, classical stable homotopy category, which is discussed in the literature very well. And also there's another fact, which I believe you will learn in the, at least you will have the knowledge to, at least, I don't know if it will actually it will be covered, but it has a T structure, but you will know what is a T structure and what is the heart of a category with infinite category with T structure, and its heart is equivalent to the nerve of the category of abelian groups. So this, at least these terms, T structure and heart, will be discussed in tomorrow's talk, I suppose. Yeah, so these are some things you are interested or you want to know about the category of spectrum. Okay. Well, then I will finish my discussion of stabilization to combine the two notions together. That is, I'm going to talk about presentable, stable infinity categories. So the idea is that if you have simultaneously stability and presentability, recall that a category is presentable if it is co-complete and it is like sort of like kind of small. So, and if you have the stable condition on it, then it is easier for you to work on the presentable infinity category. So, and a lot of co-limits and limits can be simplified greatly. And with the help of this notion, and we can complement all the results that we expected or we saw in classical story, so that we can, one of the most important of them is that you have the sigma suspension spectrum and the loop junction with infinity loop space. Well, so that what I'm basically trying to say here is that you mostly want to work with this presentable stable infinity categories. So let me write down the proposition. If C and D are presentable, and let's furthermore assume that D is a stable infinity category, then first, this is the infinity category is presentable. I have briefly talked about it because it just can be realized. It is defined as a subcategory of excisively reduced functors, and the target C is presentable. And moreover, you can, because you have the presentable categories conditions at hand, so you have adjoint functor theorems to use. So now you can prove that the infinity loop space functor has a left adjoint. And a functor between presentable categories will have a left adjoint if it preserves limits and is accessible. So anyways, so you can check that it has a left adjoint, which is the suspension spectrum functor. So this is done by using the adjoint functor theorem. And you can also relate this category C with its stabilization by following these lines of adjunctions. So a functor from the stable presentable category D to the category of spectral objects of C has a left adjoint if and only if you compose with the omega infinity functor, then this has a left adjoint. And there's a similar result that holds for the suspension infinity functor. So if furthermore C, oh, never mind. Then furthermore, you have this, oh, let me just write it in a different way. So yeah, I will explain this later. And you can precompose with the suspension infinity functor. So you will also have equivalence which reads like this. That is, so this notation means the category of functors that is a left adjoint. Functors has right adjoint. And if you are working with presentable infinity category, this is the same as functors that preserves co-limits. So if you precompose with sigma infinity plus, you also have equivalence between left adjoint functor category of left adjoint functors. And application is that if you let S be the sphere spectrum, then there is a equivalence that is the L functor from SP, the category of spectra, to D is equivalent to the category to D itself. So this is done by using the previous fact. This is equivalent to the left adjoint functors from the category of pointed spaces to D. And this equivalence is done by something like coming from the Yoneda lemma and the Prischl category. That is, this is the same as the functors from the generator, which is a point to D. So you can find this in higher topos theory. So, and what I want to say is to emphasize the importance of this result. So this result can be interpreted sort of like the category of spectra is freely generated under colimits by the sphere spectrum. And there's also a result that is the category of spaces is freely generated under colimits by a point. Okay, so finally, to end my discussion on stabilization, I want to enhance the result of presentable categories. So this is an enhancement. So we have said that last time that a category is presentable if and only if it is an accessible localization of pre-shift category of a small category, infinity category. So a category C is a presentable infinity category if and only if C is equivalent to a left exact accessible localization of some functor category to the category of spectra. So this is the stable version of the characteristic of presentable infinity categories. Yeah, so that's what I want to say about presentable stable infinity categories. Okay, so the last 5 to 10 minutes, I want to briefly discuss tensor product and how we can get smash product from tensor product. And here by tensor product, I mean the tensor product between presentable infinity categories. So I believe if not mentioned, at least we will spend a lot of time talking about monoidal infinity categories, as well as E infinity rings and A infinity rings. So I'm not going to go to that part, but I want to go down to the specific example of spectra to outline how we can define the smash product of spectra in the infinity categorical approach. So the story is like the following. So you can think about the infinity category of presentable infinity categories with left adjoint functors, that is functors that preserve colimits. So we denote this category by CAT infinity PRL. So this is our category. And it turns out that you can define a tensor product in it on this category. So namely, if you give me 2 presentable infinity categories, C1 and C2, I will define their tensor product to be the category of, well, this, let me write it first. So this is the category of functors that preserves limits. So you can do such a definition, and this is going to be a presentable category. Basically, functor categories are nice if those, because these 2 are also, they are presentable. So, and you can show that there is a bijection between these 2, well, maybe I shouldn't say bijection, but an equivalence between these 2 categories. So there's an equivalent between bilinear. I shouldn't say bilinear, but let me first write things down and explain it. There's an equivalence between these 2 categories. So where the right-hand side is the is defined, and the left-hand side means this is the functor from this product category to D, such that it is preserving colimit for each component. And this proof is a very interesting chasing or adjunctions, a very long sequence of adjunctions, and you can prove this. And yeah, and by the way, I definitely should mention the reference. So this part, Tensor Product, or this the reference is notes by it's a notes called a short course on infinity categories, and by the last name is Growth. Okay, so I apologize for not writing on the full name. But anyways, so we can prove such a thing. And this already tells us a lot. So this equivalence will give us the bilinear universal. This gives us a bilinear map from C1 times C2 to C1 tensor C2. And you can also check that the category of spaces is going to be the unit for this adjunction. Is for this monoidal product. And I'm running out of time, I'm not going to spell out the details. It is a two-sided units for it. So that is, we have this monoidal structure on this category. And now we go to the category of presentable in stable infinity category and consider the left adjoint functors between them. And we have the same tensor product. But this time, we are going to see that the spectrum, this category is going to be a unit for the monoidal structure. Because of the fact that you can check that if you have a presentable category and you tensor with this, you will get the spectrum object of C. And this tells you that the category of spectra is going to be the unit for this monoidal structure. And you can check that this will make this into a symmetric monoidal infinity category. And there is some machinery that tells you that in this case, the unit category itself has a monoidal structure. So this is the unit. So this gives you that this has a monoidal structure. And this is this is somehow uniquely defined in some sense. Yeah, actually, I don't know the full story, but you can go to Lurie's work for many details. But it will give this unit category a uniquely defined monoidal structure, and that is going to be the smash product for spectrum. Yeah, so I guess I'm running out of time, so I will stop here.